We're doing polar curves today and polar coordinates. Let me just turn some things off here. Okay, so we're going to start by learning how to represent points in a different way than we're used to. We're used to representing points in, we're using rectangular coordinates. So that's just your x and y. But today we want to describe points in the plane using an angle measure and a radial measure. Okay. So now the angular measure we're going to be using is the angle. So if you take a point in the plane and you draw a segment from the origin to that point, we make an angle with the positive x-axis. So we're going to call that angle theta. Okay. So just two notes. The angle is considered positive if we have to go counterclockwise from the positive x-axis. Okay. If, however, we decide to start at the x-axis and go clockwise, that angle is considered negative. So that's the clockwise direction. Okay, so our angle measure can be both positive or negative, depending on whether they're going counterclockwise or clockwise. And thank you for starting the recording. Okay, so we've all seen this picture before, so I'll just go through this quickly. What we want to do is we want to relate rectangular coordinates to the angle and radial measure. So using our segment, we create a right triangle, and we'll just use the first quadrant as an inspiration for the formulas. But we see that cosine of our angle is the adjacent side divided by the hypotenuse side, where r was like the radial measure or the distance to the origin, even though for today we're going to allow r to be negative as well, and we'll see what that means. So of course that implies, if you solve for x, that x is equal to r cosine theta. Similarly, using our right triangle, sine of theta would be the opposite side. So that corresponds to the y coordinate over the hypotenuse r. So that solving for y, we've found what y is in terms of r and theta. So we notice that because of the Pythagorean trig identity, we have x squared plus y squared. If you replace x with r cosine and y with r sine, and use the Pythagorean trig identity, we see that x squared plus y squared equals r squared. So r squared represents the distance squared between the point and the origin. So thirdly, we notice that if you take y divided by x and write those in terms of the polar coordinates, we get the relation that the tangent of this radial measure theta is y divided by x for our point. Okay, so these are three key formulas to know. Of course, they all derive from the first statement. Now, the question is if we know that tangent of theta is y divided by x, can we then conclude that theta is the inverse tangent, let's say arctangent of y over x? Well, this is actually not true in general. So you're not guaranteed that if you're given an x and y coordinate for a point, you can simply find the arctangent of y divided by x and get the guaranteed angle there. It's just not the case. So this would be a good point to review tangent and arctangent. Okay, so notice that tangent, the graph of y equals tangent x, it's not invertible, right? It doesn't pass the horizontal line test. It's not invertible. This is not invertible. Okay. So there is no inverse of tangent, right? However, if we restrict the domain of tangent, if we just focus on tangent just between these two vertical asymptotes, so that's at negative pi over 2 and pi over 2. If we just restrict our attention to tangent on that interval from negative pi over 2 to pi over 2, then the graph there in orange would pass the vertical line test. So tangent restricted to the interval from negative half a pi to half a pi is invertible. Okay. So what arctangent is actually the inverse of tangent, not for all possible numbers, but just the inverse of tangent on that interval from negative pi over 2 to pi over 2. So if you take this portion of this graph and just kind of flip it around, you get the graph of arctangent right here. Okay, and so the two vertical asymptotes in the graph of tangent, x equals negative pi over 2 and x equals pi over 2, become two horizontal tangents for the graph of arctangent. So those are horizontal asymptotes. Okay. So here what we want to recall is that arctangent of a number always returns a number between negative pi over 2 and pi over 2. So in terms of a circle, in the xy plane, the angle that arctangent will return is always between negative pi over 2 to pi over 2. It only returns angles in the first and fourth quadrant. It would never give you a theta that's in the second and third quadrant. So we have to keep that in mind. Okay. Well, I kind of drew a picture already, so okay. So if we are in the first or fourth quadrant, then arctangent of y over x will return a theta that's valid for our point. And so this is if x is positive, right? So if x is positive for your point, then we can go ahead and use our formula. That theta, the angle measure, can be given by arctangent of y over x. Okay. However, if we're in the second, yeah, I could do that. But if you're in the second or third quadrant, then I guess the x coordinate comes first, right, in the ordered pair. Okay. Then the formula we'd want to use is to simply add. You can still find the correct theta or a correct theta, by using arctangent of y divided by x. However, you'd either want to add pi or subtract pi. So if x is negative, then you can still use your arctangent formula to get theta, but you have to remember that you should either add or subtract pi. So as somebody pointed out, if you have, a function, say y equals f of x, if it's invertible, we sometimes write, that, okay, then x is given by the inverse of the function, and we use that -1 exponent notation of y would give you x. So that's so this notation means inverse of the function. So sometimes if you have y equals tangent x, rather loosely they'll write that, okay, the inverse of tangent is tangent to the -1 power in notation. Okay, and of course they mean that's not the inverse of tangent, but rather the inverse of tangent when the argument of tangent is the domain of tangent is restricted to -pi/2 to pi/2. Okay, but this of course is not the same thing as the reciprocal, right? So this might mean the same as arctangent of x in the sense of inverse, but that's not the same as saying tangent of x to the -1 power, right? Which would mean now reciprocal. So just a note. So these are confusing notations meaning two different things. So let's quickly, let's just do an example, right? So let's start with an example here. Okay. So I have this point, and that's a xy pair to describe a point in the plane. And I want to find the corresponding radial measures, or sorry, polar measures. So I'm starting with rectangular, and we want to find the polar coordinates. So we want to know r, and we want to know theta. Well, for our first point, we know, let's do r. We know that r squared is the same as x squared plus y squared. So r squared equals 4. So r is going to be either plus or minus 2. And I'm just going to now just take the positive measure, 2. Okay. And since here the x coordinate of our point is 1, it's positive, I can just use my arctangent formula. We're in the first quadrant. So the y coordinate is square root of 3, the x coordinate is 1, and arctangent of square root of 3 is so that's pi/3 radians, or if you'd like, it's 60 degrees. Okay, so now the point with rectangular coordinates 1 square root of 3 corresponds to is represented by the rectangular polar coordinates where r is 2 and theta is pi/3. Okay. Now, on the other hand, if we take this point over here, that's in the second quadrant, the x coordinate is now negative. So typically I just use reference angles, but I'll just use my formula. So to get theta, you can still use arctangent of y over x, but this time I either add or subtract pi. So I'm just going to add pi. I want a positive angle. So that's going to be arctangent of negative square root of 3 is negative pi over 3. We add pi. That guarantees that theta now, or I label it theta, but whatever, that our angles now correspond to some point in the second quadrant. 2 pi over 3 is theta. So the point with rectangular coordinates negative 1 square root of 3 can also be represented by the polar coordinates where r is 2 and theta is 2 pi over 3. Well, we can get to that, but it actually doesn't matter. But maybe I can answer that question. Yeah, we can answer that question with the next example. So this time I have the point using rectangular coordinates, negative 5, 5, negative 5, negative 5. So we're in the third quadrant. Okay. So if I want the polar representation of this point, where my angle is from negative pi, somewhere in the range from negative pi to pi, right? So we're talking about some angle that's, you can measure from negative pi over 2, sorry, negative pi. And then we would go in the increasing direction of theta, so counterclockwise. Here theta would be negative pi over 2. Here theta would be 0. Once we get to the positive y-axis, theta becomes positive pi over 2. And once we get back, theta would be pi. So since the x-coordinate is negative, I can get theta as arctangent of y over x. So arctangent of 1 is what we all know. Well, okay. Arctangent of 1 is pi over 4. But then we would either add or subtract pi, right? So should we add pi or subtract pi in this case? If, I should emphasize, maybe it's not clear, we're looking for our angular measure, theta, to be in that interval from negative pi to pi. Subtract, right. If you took pi over 4 plus pi, of course, then you would get 5 pi over 4, so that's not in the correct range. What that would represent would be the measure to our segment here, starting at the positive x-axis going counterclockwise. So that green measure would be 5 pi over 4. It's terrible. Okay. Right. But we were asked to find an angular measure that's in the interval from negative pi to pi, so we would be going clockwise from the positive x-axis. So we would want to subtract. So that measure is negative 3 pi over 4. Okay, very good. So on the other hand, if we wanted our, oh, and by the way, and obviously I should finish this problem. R squared is going to be x squared plus y squared. Okay. So R is going to be plus or minus 5 times square root of 2. I'm just going to take, for now, I'm just going to take the positive radial measure. Okay. So on the other hand, if we wanted our theta to be in the range from 0 to 2 pi, so not negative, I would still use my formula, but this time I would add pi, right? So theta would be 5 pi over 4. Okay. So what we have to get used to in our calculus course when dealing with polar coordinates is to be able to go back and forth between the rectangular representation of a point and polar representations. Okay. And going from polar to rectangular is actually quite easy, right? Because we have formulas. So as soon as you know r, you know theta, you can get the corresponding x and y coordinate. And furthermore, it's unique, right? There's only, given an r and a theta, there's only one point that you're going to get. Okay. Going the other way is a bit more difficult. Given a point in the plane with the x and y coordinate, if you want to write down the corresponding coordinate representation of that point, it's not unique. You can write it. You can describe the same point using polar coordinates in many different ways. So it's not unique. It might be a little bit more difficult. Okay. And we'll get to negative r values as well. Okay. So this is what we're going to focus on next, going from rectangular coordinates to polar, and why it's not unique. All right, so I think I promised myself I would try this polling thing. So it should be an easy question before we move on. Okay, so this is, I'm going to start a poll. All right, so here, this is a question that I'll give you a little bit of time to work on. So given polar coordinates, so an r and a theta value, what are the rectangular coordinates for this point? I'll give you a minute. Okay. We're getting a good number of responses, and it looks like there's a popular choice. Now, are there some obvious? So we can always, since we can, which quadrant is this point in, first of all? So if we start with the positive x-axis, and we know our angle is 2 pi divided by 3, so 2/3 of pi. So here's the first third, the second third. So that's some angle which would give us a point in the second quadrant. So that clearly eliminates some answer choices, right? Because in the second quadrant, x has to be negative and y has to be positive. So that right away eliminates a couple of the answer choices. And okay, so then we just right, we can also compute the radius, or I'm sorry, we can just use our formulas, right? Because going from polar to rectangular is easy because we have direct formulas. Okay, so the radial measure is 2, and then we get cosine of 2 pi over 3. So cosine of 2 pi over 3 is -1/2. I mean, of course, we can stop right there, but let's finish this off. Okay, so then sine of 2/3 of pi is square root of 3 over 2. Okay, so answer choice 2 was the popular answer, I'm glad to see. Okay. All right, great. So now let's look at why the polar coordinate representation of a point is not unique. And let's figure out how many different ways we can write the polar representation of a single point. Okay, so we're going to make several observations. So first of all, because cosine and sine have a period of 2 pi, right? If you have a point with a radial measure and a theta, if you let theta go all the way around, make a full revolution, so that's an additional 2 pi radians for a full revolution, you would end up at the same point on our circle, right? So it turns out that if you have r and theta to represent a point, you can always add 2 pi to that to get back to the same point, because you've just made a full revolution. And of course, you can also go the other way, right? So if you have theta, you can always go clockwise, full revolution. So minus 2 pi. So plus or minus 2 pi. And even furthermore, you can do this repeatedly, right? So you can start with theta, and then you can say go 1, 2 revolutions, and you still end up at the same position on our circle. So you can add any add or subtract any multiple, integer multiple of 2 pi. So the point where the distance 1 away from the origin, it's 45 degrees from the positive x-axis, that represents a point that can also be given by 1, and then add 2 pi to that. What is that? Yeah, 9 pi over 4. That represents the same point. Right? So we found 2 different polar representations of exactly the same point. Okay. So we're just taking advantage of the fact that sine and cosine have a period of 2 pi. Okay. So the next observation is that r can be negative, at least in calculus 2 here, right? So it's a little warning later on in other courses like engineering courses or maybe physics courses, your professors might insist that r is the distance to the origin. So some courses r will not be negative because r will represent a distance. Between a point and the origin. Right, and in those cases, we're just going to make sure that we always use a positive r value. But for your calculus course, we're going to allow r, the radial measure, to be negative, and we just have to figure out what that means. Okay, so suppose I take a point, and it has a polar representation here. R will be positive. Here's theta. Okay, so let's get theta. You can think of theta as like something that gives you the positive radial direction. So if we have theta, you can think of the game of Twister where you spin that little thing, and you have this little arrow that's pointing in the positive radial direction. So given theta, our spinner is pointing in the positive radial direction. Okay. So for example, if theta is pi over 3, okay, then we know that positive radial direction is in the first quadrant. And then the r value tells me how far out I would go from, because if the r is positive here, it would tell me that I would need to go 3 units away from the origin, right? So we would end up on a circle, despite what my graphic says, radius 3, and in the first quadrant. Okay. So if instead we have the angle is pi over 3, but the radial quantity is negative, right? what that means is that instead of going in the positive radial direction, we want to go in the opposite negative radial direction relative to that given angle, right? So if theta is pi over 3, r is negative, all we have to do is just go in the opposite direction of where the pointer is showing us to go, because we're going in the negative radial direction. So here we would end up at the point when r is positive, we end up in the first quadrant. But if r is negative, we end up at a point in the third quadrant. Which our formulas would have given us anyway, right? If you replaced r with a negative value, we would get the correct point in the correct quadrant. Okay. So r being negative means that if theta kind of tells us what the positive radial direction is, a negative r says we should go in that opposite direction to get to our point. Okay. I don't know why I have two circles. Okay. All right. So using that fact, we can now find yet another way to represent a point using polar coordinates. So let's take a point represented by polar coordinates r theta, where r is positive, say. Okay, so we're over here. So what we can do is, instead of going all the way around and making a full revolution, we can just make half a revolution. Right. So we're going to start with theta, and we're going to go make a straight edge here. So we're going to add pi, or 180 degrees. Okay. So we're going to add pi. So now, if theta is, if our angle measure is theta plus pi, that angle is indicating that the positive radial direction is opposite of what it was when we just had theta for the radial measure. Okay. So what we can do is then go in the negative r direction, radial direction, to get back to this point. Right. So I guess what I'm saying is that to get another representation of exactly the same point, you can add pi to your angle theta, and then replace r with the negative of that r. You can get back to the same point. I hope geometrically that makes sense. I don't think I explained that the clearest way. So, all right. And we can, of course, start with angle theta and a positive r value, and then just make a half revolution, but clockwise. So we can also subtract pi from theta, and then replace r with its negative to give us another representation of exactly the same point. Okay, good. Good. Okay. And then you can do this continuously. So I could, for example, take r, replace it with its negative, and instead of adding pi, make one and another half revolution, so 1.5 revolutions. So that's 3 pi, or subtract 3 pi, and so on. So there's in fact infinitely many ways to do this, right? So any odd multiple of pi. I think I had no, I guess I didn't have an example. Okay, so let's do an example. Suppose we take a point over here. And suppose that this is the point -1, -1. And this is in rectangular coordinates. My bad. -1, 1 in rectangular coordinates. Okay. So what is the polar representation of that point? What is theta? I am recording this one, yes. Okay. So here's theta, well, we would go 90 degrees plus another 45, so that's 3/4 of pi. So theta is 3/4 of pi. Okay, and the radius, if I want a positive value, would be the square root of x squared plus y squared. So square root of 2. Okay. So now if I want to represent exactly the same point, but differently using polar coordinates, I could just simply add pi, right? So what I want to do is I want to add pi to theta to get to the kind of the diametrically opposed radial direction. So half a revolution is 180 degrees or pi radians. And replace this radial measure with the negative of it. Right? So the negative square root of 2. Okay. So let's see if that indeed works. So I would go 1/4, 2/4, 3/4, 4, 5/4, 6, 7/4 of pi. But because r is negative, instead of going in the positive radial direction, I would go in the opposite negative radial direction, negative square root of 2, and I would end up at the same point. Okay. And of course, there's infinitely many of these, so I could have as well started with the original theta, then subtract pi. Maybe I can use green. Yeah, okay. So start with theta, and then subtract pi. That's half a revolution clockwise. And they see it would end up kind of at the same radial direction. To get 3 pi over 4, we add pi, right? To get 3 pi over 4, we added pi. No, we got 3 pi over 4 here, just from our knowledge of the unit circle. That was like that's something just being familiar with the unit circle. Right. So we knew where our point was, -1, 1. And we know theta can be measured from the positive axis counterclockwise. So we knew that that was 1, 2, 3/4 of pi. So that's just knowing the unit circle. Oh, yeah, thank you. So what you're saying is, yeah, so we had a formula for like when the x coordinate is negative, if we want a formula, that theta is arctangent of y over x, let's say plus pi. So arctangent of y over x plus pi, arctangent of -1 is negative pi over 4 plus pi. Indeed, that would give us 3 pi over 4. Very good. Okay. I think that's all I had for that. Okay. I'm not getting very far, it looks like. Okay. But maybe it's more important to get the fundamentals of, just getting familiar with polar coordinates. So I might not get through everything, but okay. I have another poll question. Okay. So this time we're given the rectangular coordinates for the point. And we know that there's many polar coordinate representations of this point. So which of the following 5 is invalid? So all these are correct except one. So I want you to find the incorrect one. Yeah, so this is a little rougher because now, of course, we could just confirm, right? You can check each of the 5 answer choices using our formula. Of course, we don't want to do that. We want to do this more conceptually. So we could just go through the 5 answer choices and plug the r and the theta values into our formulas to see that we get the correct. But maybe we just want to think about this. So we see that our point is in the third quadrant, sorry, because both the x and the y coordinate are negative. The radius is plus, our point lies on a circle of radius 4. And so our theta measure can be given by, it's not unique, of course, so arctangent of y over x. And we'll just add pi to this because the x coordinate is negative. I guess that's going to be, I did something wrong, I think. So that's going to be 7 pi over pi over 6. Even if you use a calculator, right? That's what you get. So 7 pi over 6. So our point is over here. Okay. But of course, I could describe that same position if I use a negative angle. So if I start with the positive x-axis and go clockwise, that's going to be 1, 2, 3, 4, 5. So negative 5 pi over 6. So this works as well. So that works. Now the third one works because I could go counterclockwise, and that's 13 pi over 6. So that's 2 pi plus another 1/6 of pi, which would we would end up being over here somewhere. That's the positive radial direction. Okay. But because here r is -4, instead of going in the positive radial direction for that angle, we would go in the opposite negative direction, and we would end up at the same point. Okay, very good. And so the last one is incorrect because, let's see, let me do that one in green. So if our theta is negative pi over 6, that green segment ray would indicate the positive radial direction. But r is -4, so we go in the opposite direction, and we would not end up at the correct place. Okay, very good. Good. It looks like most people answered. Got it. All right, so next we're going to look at polar equations. So this is where r is given as a function of theta. So given theta, r tells you how far out to go from the origin, either in the positive radial direction, negative radial direction, depending on the function f. And then you want to recall that we can always relate that to x and y by using our formulas x equals r cosine and y equals r sine, where r just happens to be a function of theta this time. So what I want to do here is, now when I say what we're going to be doing is maybe, okay, starting with polar equation, so r equals f of theta, what we want to do is rewrite this in rectangular coordinates. So you want to get an equation in rectangular coordinates. Okay. And what we always want to do is take advantage of these two facts, right? Okay. And fact that x squared plus y squared equals r squared. So if you have a polar equation and you see a sign, like in this next example, you know that if you multiply that by r, you would get r sine. So let's multiply both sides by r, just so that we can take advantage of the fact that r times sine theta is y, and we know that r squared is x squared plus y squared. Is that clear? That I anticipated that I could take advantage of these facts. I just had to multiply the sign by an r, right? So, okay. And so we see that, I guess if I bring everything to one side and complete the square here, so I'm completing the square. Okay. Our polar equation, where r equals 2 times sine theta, corresponds to an equation using rectangular coordinates, which we recognize as a circle with center 0, 1, with radius 1. So that gives us a circle. Okay, so let's do the next example. R equals 3. So what's the corresponding equation in rectangular coordinates? Well, here we just directly take advantage of this fact, right? So here r is positive, so take the square root. So r is equal to the square root of x squared plus y squared. And that's equal to 3. So we recognize that as an equation of a circle centered at the origin of radius 3. So representing a circle centered at the origin is very simple using polar coordinates, right? Because it's just the set of all points in the plane whose distance to the origin is always 3, so that almost geometrically, right, by definition, is a circle of radius 3. So I'll go ahead and move on to the next example. So we have theta equals 3 pi over 4. So let's just think this one through, right? What's the graph of an equation? The graph of an equation is all points that satisfy that equation. So I'm looking, let me just draw that angle, 3 pi over 4. Okay. And so we're looking at all points such that the radial measure is 3 pi over 4. So it's clearly all points on this diagonal line. And I'm drawing an array where r is positive. but because we're allowing r to be negative as well, if we given this angle, we can go in the negative radial direction as well. And so we anticipate that this would be the line y equals the negative of x. If you want to take advantage of formulas, we know that tangent of theta is y divided by x. So if we have that theta is 3 pi over 4, tangent of theta, what's tangent of 3 pi over 4? Is negative 1, right? I'll write that out. So we just take the tangent of both sides. And tangent of theta is y over x. Tangent of 3 pi over 4 is negative 1. So y equals the negative of x. So representing a line through the origin is also simple, because if you take any line through the origin, the theta value is always constant. Okay, I'll skip the next example and go to this one really quickly. So I'll also want to write this in rectangular coordinates. So what we have is that r squared is cosine 2 theta. All right, so first, if I want to take advantage of our formulas, because I want to introduce x and y, I would have to first use a trig identity on this, cosine of 2 theta, right? We want to see cosine of theta instead, so that we can use our formula. We can recall the formula for cosine of 2 theta. That's equivalent to cosine squared of theta minus sine squared of theta. Okay, so let's rewrite that. Okay, and now to use our formulas, we'd want to multiply both sides by r squared. Because then r to the power 4, well, that's r squared squared. So r squared is x squared plus y squared. That whole thing squared would be equal to x squared minus y squared. Okay, and this, if I look at this equation in rectangular coordinates, I don't recognize what the graph of that is at all. In fact, it's this infinity kind of symbol looking thing. It's a bow tie looking thing. So we can't always, write down the rectangular equation corresponding to our polar equation and recognize what it looks like. We would have to learn how to graph those some other way. Okay, so I believe, in fact, that, let's see if that's I'll skip this next poll question and just move on to graphing polar curves, right? So you're going to be expected to graph some kind of standard polar curves, okay? So we're going to look at this polar equation and we want to graph it. So now when we say graph it, we're going to graph it in the xy plane, right? So we want to graph that equation, but in the xy plane. And I want to distinguish that from graphing that equation in some kind of r theta plane, right? Because that would be easy. If you have r versus theta, and theta being your horizontal and r being your vertical axes, and if you wanted to graph this equation, you know how to graph sine versus sine of theta versus r, right? You would get Does anybody know what the period of this function is? Sine. All right, great. Okay. So just a quick not a conceptual thing, but I guess a formulaic thing. If you have a sine of k theta or cosine of k theta, how do you find the principal period of those two basic trig functions? Okay, am I still too quiet?
Isn't it like 2 pi over k?
Yes. So the period is the principal period of, basic period of a sine or cosine divided by that number k. Okay. So here we can anticipate that the period of this function is 2 pi divided by k, or 2. So it's pi. Right, so what I can do is I can draw a period of a basic sine function, one period of it, but that's going to be from 0 to pi. Okay, and then I can draw another one, like a period of sine that goes from pi to 2 pi. And once I get to 2 pi, I know that I have enough graph to give me the correct polar curve in the xy plane. Okay. All right. And so notice that my sine function, well, what's the amplitude, okay, of my sine function? It's 3. So the sine function will oscillate between -3 and 3. All right. And here, whenever our sine function crosses the horizontal axis, that's a place where r equals 0, correct? So that means an r equals 0 means we're at the origin because we're a distance of 0 away from the origin. Okay. So when theta is 0, we're at the origin because r is 0. And as theta increases, our radius is increasing, pi over 4. Our radius is increasing until we reach the highest point at pi over 4. Okay, and then our radius will decrease until we get once we get to pi over 2. Okay, so we start with r being 0, so we're at the origin. Then r increases when at pi over 4 r is equal to 3, and then r starts decreasing when at pi over 2 we get back to the origin because r is 0. So, and notice here r is positive, right? So that part of our sine function corresponds to this kind of pedal-looking thing in the xy plane. Because r started being 0, then r increased until we get to r equals 3, and then r started decreasing when we get to pi over 2, we're back at the origin because r is 0. Okay. So next we consider the angles, theta being between pi over 2 and pi. Okay. Here notice that r is negative, right? So instead of going in the positive radial direction and for those angles, we go in the opposite direction. But once again, we're going to start with r being 0 when our angle is pi over 2. And when the angle is 3 pi over 4, r is -3, so we go in the opposite direction. Okay, so r starts being at 0, increases, and then decreases back to 0. So this part of the graph here, and the r theta plane corresponds to this pedal for our polar graph in the xy plane. Okay, so the next angles we want to consider are in the third quadrant, where theta is between pi and 5 pi over 4. Here the r values are positive, so we're going to go positive radial direction, starting with r equals 0. And once we get to 5 pi over 4, r is at its maximum of 3, and then we go back to 0. Okay. So this portion here corresponds to this pedal. So finally, we're looking at angles between 5 pi over 4 and 2 pi. But here the r values are negative, so when we draw our kind of radial lines, it's going to be negative radial direction, so this way. So this piece corresponds to this fourth pedal. And if you go past that, we just start covering the same curve again. So we just kind of, right, if you try to graph further, you would get that this part corresponds to exactly the same pedal, the orange pedal that we have. This part would correspond to the exact same green pedal, and so on. Okay. So it'd be covering the same curve. Now, another way to deal with this is to realize that, okay, so this is going to be a family of polar curves that are in the form r is equal to some multiple of sine of k theta, or r equals to a multiple of cosine k theta, right? So a is the amplitude, and 2 pi over k would represent a period. And these are called rose curves for obvious reasons, right? They look like petals of flowers. So to deal with such rose curves, what you could have done is kind of realize that we're going to get petals, and each petal is a single petal is defined by two places, two consecutive values of theta, where r is 0, right? Because you get a petal where r is 0 and then r is 0 again, that's going to correspond to a single petal. And then you also have places where the r value is maximized or minimized. So those like extreme points. So those correspond to the tips of the petals. Well, I lost my way. Okay. So if you're dealing with a rose curve, you can just figure out the values of theta where r is 0. And number 2, figure out thetas, or find thetas I could have just written, where r is maximized or minimized. So where sine or cosine are plus or minus 1. Okay. So we can maybe use that method for the next example. Right. So let's look at another rose curve. So here we have the amplitude is 1. Okay. So we're going to find all the places where, let's say, do peaks. So we know that cosine of 3 theta is always some value between -1 and 1. Yeah, that's the range of our basic cosine function. So when is cosine equal to plus or minus 1? What has to be true about the argument of cosine, right? Well, we know that cosine is 1 if our angle is 0, 2 pi, 4 pi, and so on, and it's equal to, and cosine is -1 when the argument is pi or 3 pi, and so on. So for cosine to be plus or minus 1, the argument has to be a multiple of pi. So 0, pi, 2 pi, and so on. Okay, so then in order to actually solve for theta, we want to divide everything by 3. And so here this is gonna give us the values of theta where we have the tip of the pedal, right? So at theta equals 0, right? Cosine of 0 would be 1. Okay. When theta is pi over 3, cosine of 3 times pi over 3, it's cosine of pi, so that's -1. So at pi over 3, the r value would be -1, so we actually want to go in the opposite direction to get the tip of our next pedal. So these are tips of our pedal. Okay, and when theta is 2 pi over 3, cosine of that 3 times that angle gives us 1. So 2 pi over 3, r is 1. So that's the next tip of the pedal. And then when theta is pi, cosine of 3 times theta will give us -1. So you see it's kind of alternating. So when theta is pi, r is -1. So we would actually end up back over here, right? So those are the those are the tips of our pedal, and you just keep going like that. So next, maybe we want to find where r is 0, because 2 consecutive values of theta where r is 0 defines a single pedal of our rose curve. So where's cosine of 3 theta equal to 0? Well, that's when the argument of our cosine function is like pi over 2, 3 pi over 2, and so on. Right. Okay, so solving for theta by dividing by 3. Oh boy. So I guess I'm going too slowly, huh? Oh, okay. Okay. Anyway, here we have, I could have also included negative pi over 2 for convenience. So our first pedal would happen between when theta is negative pi over 6, and then positive 2 pi over 6. So those are 2 consecutive values of theta where r is 0, so that's going to define a single pedal of our rose curve. The next 2 places is between pi over 6 and pi over 2, but there r was negative, so there you go. And next 2 places, 5 pi over pi over 2 and 5 pi over 6. So that defines the next pedal. Okay, and then we just keep repeating like that. And of course, you could have always done the kind of standard thing and just picked typical values of theta and start plotting the r values, or finding the r values and then plotting those points. Okay. So, you know, it's going to be a semester, so I'll let you'll learn in class how to, you'll have more practice during the semester. I just wanted to give you a flavor of this, so, okay. So let's actually move on to another topic. Okay. So because we have curves, right, and we're in calculus, typical problem is to find tangent lines to curves. So we want to do that for polar curves as well. Okay, so remember that we get a polar equation where r is a function of theta. We also remember that that's related to x and y. Now, if r is a function of theta, and then we multiply that by cosine theta, ultimately x is a function of theta. So you can think of theta as a parameter, but it's more specific, right? Theta has a geometric meaning in the xy plane. It's an angle measured from the positive x-axis. So, and likewise for y. Y is a function of theta, right? So we get a parametric curve where the parameter is theta. So if we wanted to find slopes of tangent lines, we want to find dy dx. And we recall from the parametric curves camp that you can get that by finding dy d theta and divided by dx d theta. Okay. So what you would do is you'd use to differentiate y with respect to theta, just use product rule, because remember r is a function of theta, sine of theta is a function of theta, so you have to use product rule. So in the numerator, you just take turns differentiating the two factors. So r prime times sine plus r times the derivative of sine is cosine. Okay. And in the denominator, you want to differentiate x with respect to theta, but x, you know, you get a product of two functions of theta, so product rule. So r prime, leave cosine alone, then plus r, then differentiate cosine with respect to theta to get negative sine. Okay, so this formula for dy dx when dealing with a parametric curve, in a sense, you already know. For a polar curve, in a sense, you already know if you know the formula for dy dx for a parametric curve. Okay, so you'll be using that as well. So as an example, let's just keep it really simple. Suppose we get a polar curve where r is equal to 1 over theta for positive theta, say. So that's going to look like some sort of spiral. If theta is close to 0, then 1 over theta is large, so r is large. And then as theta increases, r should be getting smaller, so it's some kind of weird combination of snail and spiral, right? And as theta goes to infinity, we start approaching the origin. And we want to find equation of a tangent line to this polar curve, specifically when theta equals pi. Okay, so we would want to find a point. So we want tangent line. So of course we need a point of tangency and we need a slope. The point we get because we know that x is equal to r cosine theta. And specifically when theta is pi, so we get negative 1 over pi. What time is it? Oh boy. So y is equal to r, 1 over theta, times sine theta, evaluated specifically at pi, so we get 0. Okay, so Okay, so that the point corresponding to something. Oh yeah, that makes sense. We're over here. My bad. So that's a negative x coordinate and 0 y coordinate. Now I don't think that that's the tangent is going to be vertical necessarily. I could have just drawn that incorrectly or not quite correctly. So next you want a slope. So we want to find dy dx specifically at theta equals pi. So we just use our formula for dy dx when given a polar curve. Okay. So r prime sine plus r cosine divided by r prime cosine minus r sine. Evaluated at theta equals pi. So we get now sine of pi is 0, so that's going to simplify some stuff. So the slope is negative pi. Okay. And so there we go. We have a point and we have a slope. So if I didn't draw that very well. Oops, I didn't mean to erase all of it. Okay. Why does it erase the whole spiral? Okay. But at our point, we have a negative slope of negative pi. It's pretty steep, I guess. And our equation would be y minus the y coordinate of our point of tangency. Slope times x minus the x coordinate of point of tangency. Okay, so I only have 3 minutes. So what I'm going to do is just talk about the formulas you'll be studying. So you'll also be studying arc length for polar curves, because of course, for a polar curve, you can always think of that as a parametrization of x and y in terms of theta. And so you already have a formula for the arc length given a parametric curve that if you were here yesterday, you'd know, right? Except we replace t with our specific parameter theta. So we're going to get the differential arc length element as the square root of dx d theta squared plus dy d theta squared d theta. And since x is r cosine, differentiating that with respect to x and remembering that r is a function of theta, or differentiate with respect to theta, sorry, and remembering that r is a function of theta, we use product rule to differentiate. And likewise for y. We use product rule. And then we would have to square those derivatives. Okay, and I guess to make the story short, you would use Pythagorean trig identity, and you would get a formula for the differential arc length element when you have a polar curve. Okay, so you might want to try that, actually squaring these derivatives, recombining things, and using Pythagorean trig identity to get this reduced formula for arc length, the differential arc length. Okay, so Elliot linked to a survey. We would appreciate if you give us your feedback. And I also didn't get to formulas for area, but I'll let your professor, well, do their job for you, right? All right, thank you so much.